Okay, so we want to look at an example of how we can use the basic form for Newton's law of cooling and get a specific model. Now remember, Newton's law of cooling starts off like this. The change in temperature over time. So this is our initial model. And we found that we could go through and solve this, and what we get is we get T minus TR is equal to H e to the KT. This is what we found. Now we want to look at a specific example here. So let's suppose, and we make some assumptions. We're assuming that the surrounding temperature does not change. What changes is whatever's being cooled. So let's just suppose, we can say this. We can say, okay, we've got something that's 100 degrees Celsius. Okay? So let's suppose that we've got something, and this is the initial temperature. So this is the initial temperature, and it's 100 degrees Celsius. We'll take that as an assumption. And then let's say this. Let's suppose that the surrounding temperature is 30 degrees Celsius. So let's just make that assumption. Now, so we have this object, it's 100 degrees Celsius. We immediately take it away from the heat source or whatever and put it in this environment that's kept at a constant 30 degrees Celsius. That's the room temperature. Now, we need one more bit of information. Let's suppose that after, let's say, 10 minutes, let's suppose that after 10 minutes, the temperature is now 80 degrees Celsius. So that's another bit of information we need, because what we have here is we have two constants. So I need two bits of information. Okay, now I'm going to use this first bit of information here. Now, the surrounding temperature is 30 degrees, so we can immediately just put that in. So our model immediately becomes T minus 30. And let me just leave off the degree symbol and everything. We've got T minus 30 equals H e to the KT. So we can do that, because that TR is not a variable. It's just fixed. Now, we know this, that after 10 minutes, the temperature is 80 degrees Celsius, right? 80 degrees Celsius. Okay, so let's see what we've got here. So after 10 minutes, we've got this. We've got 80 minus 30 equals H e to the 10K. Okay. Everybody see that? Okay, now, I forgot to solve for the H, didn't I? I forgot to solve for the H. Let me go back. Let me go back then and say, okay, this is one of the things that we have, right? After 10 minutes, we have this, right? Well, when time is 0, what do we have? When time is 0, we have this. We have 100 minus 30 equals H e to the 0K, right? Okay. See, okay. Okay, so what does H equal? H equals 70. That's right, 70. Okay. Okay, so we got that. We got one of those constants. Now I can come over here and get this other one. So this over here is going to be 50. This over here is going to be 70 e to the 10K. Yeah, that's right. Now I can divide by 70, because now our job is to simply solve for K, because we needed H and we needed K. Now, you might observe that H is going to be the difference between the initial temperature and the room temperature. If you make that observation, that's good. That might save you some time. So let's see what we've got. We've got 5/7. Okay, so this is 5/7 equals e to the 10K. Now I'm going to log both sides. Like that. And then I divide by 10. And now we have a formula for K. So we take the log of 5/7 and we divide by 10. And it looks like our K is going to be negative. I'll just round that way. Negative 0.0336. Everybody see that? Now, what we've done here is we've used Newton's law of cooling and we've come up with a model. So here's what we've got. We've got T. Now remember the room temperature, we had T minus 30. So let me go ahead and bring that to the other side and just call it 30. Plus, this was 70, e to the negative 0.0336 T. And that is our Newton's law of cooling formula. Now, let me ask you this. What happens as T goes to infinity? Just think about this limit. You have e to a negative power with T on it. What happens as T goes to infinity? Well, what happens to this term right here as T goes to infinity? It goes to 0. So it looks like as T goes to infinity, our temperature goes to the room temperature, right? Now let's look at that. We can real quickly look at that graphically. It won't take but a minute. We can take, what was it? We had 30 plus 70, and then e to the negative 0.0336 T. And let me set my window. Set my window from 0, I don't know, maybe 10. Well, let me make it 100. And what was the initial temperature? 100? Or yeah, 100. So let me make this maybe 110. Okay. Let's see if we can get a look at the graph. Okay, so there's what it looks like, right? Now, remember we said the room temperature was 30. So let me go ahead and put a 30 down here. And you see the horizontal asymptote there, right? So this curve, you can see it really, the steepness of the curve, it gets less steep over time as it gets closer and closer to room temperature. So this is Newton's law of cooling. Any questions about that?